He just came in. Also, can we give a round of applause to Mr. Mink for helping all of your awesome projects? And you'll let me know up there. He can. I don't know who is up there. I don't know. I'm assuming he'll. Oh, okay. Oh, jeez. Okay. Here we go. Okay. Ready? I'm just going to introduce everyone. Good morning, and welcome to our final senior capstone presentations for fall of 2023. Again, I would like to give a round of applause to our awesome seniors for making it this far. They will now become, hopefully, by the end of this semester, if not next semester, mechanical engineers. So a round of applause to our awesome seniors. They have spent less than 15 weeks to actually develop, design, and deliver on a product for a client. And today you will be witnessing some of these amazing presentations, and also they will be showing off their products in the atrium. Even though they may not be fully complete, they will be able to give you an understanding of where they will be in the next couple of weeks after they're finished. I'm really proud of these individuals. I've seen many of them since the beginning as they entered UMBC, and now I get the awesome pleasure of kind of helping them complete their journey and watch them go off and do amazing things. I'm really, really proud of them. Thank you all for coming today. This is that because of you and your support, without you as well, and our companies and our visitors and our parents and our community. Can we give a round of applause to our parents and our families who support our students? They would not be able to get this far. My name is Dr. Jamie Gerganis. I am faculty in our engineering and computing education program, but I'm also affiliate with the mechanical engineering department. And so this is one of my favorite classes to teach and to run. And I'm also joined by our full professor who just joined us this semester, Dr. Van Lockett, who is also part of our design team as well. So without further ado, I'm going to go ahead and not keep talking and turn this over to the stars of our show today, and just go ahead and let them go, and they will get 8 minutes. And please feel free online to ask questions. We will have a couple minutes of questions. We do have our, thank you to American Society of Mechanical Engineers for joining us today as well. Give them a round of applause. And they will also be joining us at the atrium to see all the product demos as well. They spend their day volunteering to also judge, and today they will be selecting a best presentation and a best project as well, which I think you all deserve a best project. I mean, not that I'm biased or anything. Okay, so without further ado, go ahead and get started, and I will turn this over to y'all.
Good morning, everyone, and welcome to our final presentation. We are Group 1. My name is Jacob Murphy. That's Christian Soto, Adam Peck, and Daniel Shaner, and our project is called the Rotating Tester Gyro. So a little bit about our customer. Our customer is Dr. Goel. He is a controls professor here at UMBC, and he has asked us to create a device that would take one of the quadcopters in his lab and secure it to a structure, and as the quadcopter is powered and maneuvering, the orientation about 3 orthogonal axes will be measured. So the key requirement for our system is for there to be no obstruction to any rotation, because that would ruin the orientation data. We also want it to be user-friendly, so we want the user to be able to attach and detach the quadcopter within 1 minute. And some of the other electrical requirements include the use of encoders that can measure up to an accuracy of 1/2 of a degree, and for the encoder data to be recorded at a rate of 1 kilohertz. So as you can see here, we have our 2 prototypes. The first prototype, made out of Legos, was really just to get a visual understanding of our project, whereas the second prototype was a full-scale CAD model, and this really gave us insight into material quantities, in addition to being able to use that to perform analysis on to get to our final design.
Thank you, Jacob. So with this prototype 2, we then needed to run some analysis. We first wanted to understand how the motors on the quadcopter and the vibration induced by them would affect the structure. So we ran a modal analysis on a simplified model of prototype 2, Simplified because without the simplifications, the program would just crash because 3 moving axes is not going to be able to work on our hardware. And so we put this into SolidWorks, ran the modal analysis, and the data table on the right shows the natural frequencies of our structure. The natural frequencies are fairly low, and when converted over to RPMs, they are actually lower than the lowest RPM rating of the motors on board the quadcopter, which led the team to the conclusion that resonance would not be an issue with our current design. We then ran a deflection analysis where we assumed that the quadcopter is perpendicular to the ground and powered at 100% thrust. There are 2 connection points to this quadcopter in the structure, and for that reason, the force is going to be distributed across those 2 points, so it's equivalent to 2 of the motors operating at 100% thrust at the top of the structure. And because of that, you see the arrows on the left 2 images. That is where we applied a load, and we ran this analysis for no support, half support, and full supports, and the images on the left are for no supports and full supports. We took this data and plotted it on the plot on the left and fit a line through these 3 data points. This way we could pull out the deflection at the top of the structure based on any support height without needing to rerun the FEA every time. The plot on the right shows the linear correlation between encoder error and deflection at the top of the structure. And with these 2 pieces of information, along with geometric constraints of our structure, we determined that an 831 millimeter support height would be sufficient, as it would reduce the encoder error overall to 0.12 degrees, which is below the accuracy of the encoders currently on board, which is 0.5 degrees.
So our final design consists of 3 rotating rings and an outer structure. That inner rectangular ring has 4 clamps attached to it so that we can clip the quadcopter into place for testing. That middle ring has an octagonal design in order to minimize the footprint of our device. There's also 2 interfaces between each of the rings and between the outer ring and the overall structure. So we also implemented our analysis that we did on prototype 2 by adding supports onto the structure in order to minimize deflection at the top of our device. So here you can see our actual physical device. This GIF is here just to show you exactly how it moves and operates. So in terms of fabrication, we have completed our mechanical side of things. So all the mechanical devices and components are assembled. We've also completely integrated all of the electrical hardware and wired all that up. All that's left to do is finish the software side of things. And that's just creating a program that takes the encoder readings and feeds them into MATLAB to be displayed in real time. So far, we've manually maneuvered the rings in order to ensure that there's no obstructions to their rotation, also to ensure that they rotate easily and smoothly. And in the future, we plan on recording the time it takes for a user to both mount and dismount the quadcopter from our device. And here is just a basic breakdown of our budget. You can see structure takes up most of it. That structure includes the aluminum extrusions and all the mounting hardware. And then the electrical side of things also takes up a large portion. Most of that is from the encoders and the slip rings that we used.
So for the electronics, the big challenge faced was that Dr. Goel wanted this device to be able to spin in 360 degrees on all axes, which meant that cables were not an option, so we had to pick a slip ring. Dr. Goel has had some negative experiences with slip rings that are on the cheaper side, less than several $1,000s in the past, so he wanted us to pick a few that were available at a budget and then run tests on them to figure out if they were going to meet the specification required. So we picked a few, tested them, and then picked the best one. It's worth noting that the one we picked performed the best, but also had gold plates on all of the contact surfaces, which is known to be good for longevity. And then a general layout of the electronics is the encoder data runs through the slip rings and then into an Arduino that processes the data, and then it sends it through serial into MATLAB. And then the general timeline was early September, meeting with Dr. Goel and figuring out exactly what he wanted, as well as doing market research to figure out what exactly is available and kind of how other people go about it. Then in October, we started working on CAD models and doing prototypes like the first prototype you've seen, and really figuring out, okay, what exactly is this going to take? And then as November rolled around, we're ordering parts, we're testing parts, and we're starting to print and manufacture things. And then in December, in the late parts of December, we're finishing manufacturing, doing all the wiring, and we're currently in the process of finishing up the software and writing all the documentation that will go along with the use of this actual device.
Now we'll open up the floor to any questions. 。 . . . 。 . 。 . . . . . . . . . 。 . . . 。 . . . . . . . 。 . . . . . . 。 . . 。 . . . .
。 . . 。 .
. . . . . .
Excellent presentation. Just one quick question. So you had a specific copter that you were doing your design for. Did your team give any thought to if there were other models that your professor might want to use in the future and how your design could adapt to those other model quadcopters?
Absolutely. We did think about the capability of it being able to mount other quadcopters. Because of the time constraints, we decided to just focus on the one quadcopter that the professor wanted us to mount onto the frame. But in the future, mounts can be created because the 2020 is such a easily accessible and you can create parts for it pretty quickly. It would be easy to create a mounting hardware that could accept multiple different types of quadcopter arms.
Thank you.
When you tested the slip rings, what were you looking for? How'd you test the slip rings?
So there was 2 tests performed. The first one was pretty rudimentary. Basically, I was just hooking up a voltmeter to it, and I was measuring the ohms reading out. And basically, we spin it, and we were seeing if there was a drastic change in ohms. And then the second test done was basically hooked up an Arduino, and the signal runs through the encoder and then back out another wire through the encoder. And basically, the Arduino was just sending high-low signals, alternating really quickly, and then on another pin, the signal was coming back in, and it was recording whether or not it was seeing the signal that it was sending coming back in. And during that test, again, it's spun back and forth to see if anything was missed. So.
Okay, and then the encoders, are those active or passive?
I'm not familiar with that term, but they're incremental
Sure.
encoders. So they have
Okay.
transistors in that turn on or off, so it's a high or low signal coming out of them.
Okay, thanks. And I might have missed this. I saw you did some finite element analysis, and I saw the modal analysis and the frequency analysis. Usually in that, you put, and that's for the overall structure, but I was curious about the compliance of the structure and or the accuracy needed. I'm trying to compare what the customer wants and what you're providing. I understand they're keeping away from resonant frequencies is something that's paramount, but I guess I have 2 questions. The compliance of the overall structure, and does it meet the requirements associated with measurement accuracy? And then number 2, in that resonant frequency analysis, I would think that the mass that you put inside the structure, so whatever quadcopter, would enter into that frequency analysis, but maybe I'm mistaken. That's good.
I think in terms of the frequency analysis, we really were more focused on the structure, and I do get the point that the quadcopter itself would add to the overall complexity of the structure. And so when we were doing the finite element analysis for the modal analysis, we really just wanted to make sure that the motor's vibration in terms of the rotation was below or was not within the range of the resonant frequencies of the structure. And so as long as those 2 did not match up in any way, then we were okay on that end. And the first question you said was the measurement.
Compliance, like how stiff the overall, what kind of forces and everything you'll see from the quadcopter imparting on the structure and how it might deflect.
Yeah, and so that was done with the assumption that the quadcopter was going to be, at the worst case scenario, fully perpendicular to the structure and then 100% powered on. And we could find the data of each motor and then figure out the amount of thrust that it could produce based on the blade size. And so we just used that thrust, converted that to the force, and then distributed along the top of the structure and figured out the deflection that way.
Okay, thank you.
So we have one question online. Well, first you got good job team, and I think Dr. Goel is also very impressed. I was waiting for his comment. But the Eris from University of Maryland, College Park asked have you considered what happens as you power up? The system will pass through natural frequency before it reaches its operating frequency.
And so because of the specs that we were able to get from the motor manufacturer, we were able to see that even at the lowest speed, when you turn it on, there's a voltage that's actually going to start spinning the motor, and even at that lowest speed, it would not pass through the natural frequencies of the structure. Hence, we weren't worried about, or the conclusion that we came to was that it would not pass through those resonant frequencies as it even powered up.
And to kind of add on to that, so I see the person's point with as it's powering up. The motors power up relatively quickly, and it will only pass through those resonant frequencies very momentarily on startup, and testing won't be taking place during startup. So we figured that that wouldn't come into too large of a play, as it would exceed the resonant frequencies, and the system would have time to settle before that testing actually started.
All right, can we give them a round of applause? Great job, team. And team number 2, you can come on out. You gotta make sure that you hold it towards her. And don't go too
far. Ready. Good morning, everyone. This is Team Anemogenetrius of Ahmed,
I'm Kwa.
I'm Nathaniel.
And I'm Nicholas.
and we're presenting to you the coaxial counter-rotating vertical axis wind turbine. Led by our mechanical engineering faculty, Dr. Malin Yu, our team has been designated to develop a model of a vertical wind turbine made up of 2 rotors that are supposed to be rotating in opposite directions, clockwise and counterclockwise, to produce an output of 12 volts. So this model we're looking at here is of a previous semester's group project progress. We treated it as our visual reference because it has parts such as a Darius blade, which is based on its shape being airfoil shaped. It will keep the rotors flowing easily through the air, and Savonius blades as well that would help the system get self-started because of its cupping shape, as well as a motor that will be right between the rotors here, not only to generate, but also it will keep the full system in balance, being secured in place. And right here, these are the shapes of our Savonius and Darius blades, as well as their dimensions, and the dimensions of the full turbine being all in relation to each other according to the NACA 0012 airfoil ratios used.
In order for our turbine to work, we just had to purchase a few parts since most of our turbine will be 3D printed using PLA+. We first got 2 ball bearings, an AC generator, and a slip ring to connect to the generator. The overall design is what you see here in figure 7, which shows 2 vertical axis turbines mounted on top of each other. It's designed that the top turbine is able to be removed so that the double turbine will be compared to the single turbine in voltage output. It's important to note the orientation of the blades of each turbine is opposite to each other. For example, the orientation of the Savonius blades and the Darius blades is opposite to that of the top turbine is opposite to that of the bottom turbine. This is a key factor in helping the turbines spin opposite of each other when the wind blows. Figure 8 shows the generator mounted in between the 2 turbines, with the top turbine connected to the output rotor shaft of the generator and the bottom turbine connected to the stator plate of the generator. Thus, when the top turbine spins, it spins the rotor, and when the bottom turbine spins, it spins the stator. Figure 9 shows the slip ring housing, which is mounted inside the bottom turbine and is connected to the generator. Here's a motion study. Well, it's supposed to be a motion study that shows the turbine rotating counter to each other. And the theory behind this is that, according to Faraday's law, the change in magnetic flux over time, an increase in the change of magnetic flux, creates an increase in voltage. So as the rotor spins against the stator, the magnetic flux is increasing, and it's increasing the voltage. This gives us an advantage of just regular generators that have a stationary stator and a rotating rotor. As you can see, that's how it's working. So the top turbine rotates against the bottom turbine, as I just explained.
And in order to predict the performance of our system right here, we had to conduct a series of calculations to determine our outputs, either power and voltage. With a power generated of 1.5 watts and 9.262 volts at minimum, we conducted that through a series of equations used in the next slide, where
first they had to determine the area, the swept area of our turbine as it spins, and then from there calculated the power of the wind. Separately, calculating our efficiency of 39%, which is in the range of wind turbines between 30 to 40% efficiency, and then using both to calculate for an output of 1.48 watts, rounded to 1.5 watts.
We ran simulations and analyses on our system to make sure that our parts did not fail when the system was in use. Considering most of our system is made up out of 3D printed parts, once we created all of our parts, we made sure that the parts were compatible with each other, so we made sub-assemblies to make sure that they did the function that they were made to do. And with all these sub-assemblies, we created a complete system and then started testing our complete system. Over here on the left, we have a flow simulation. We have 3 meter per second wind hitting our system. And from this simulation, we saw that we had a force of 0.13 pounds-feet and a torque of 3.1 pounds-feet inches acting on our system. And with this data, we conducted an FEA on our Darius blade to make sure that it did not fail. And as we can see, it was well below the yield strength. Over here are a few of our sub-assemblies. On the left, we have our ball bearing with our shaft, and on the right, we have our AC generator connected to our stator base. And over here, we have a few sub-assemblies of the 2 different blades that we'll be using throughout our system. Lastly, with all of our sub-assemblies created, we have our complete system, as you can see here, standing on top of the oscilloscope that we use to record our data.
We tested our system with a physical fan wall and a wind simulator in SolidWorks at a wind speed of 3 meters per second, and the voltage was recorded by using a multimeter. We also connected the wires of the system to an oscilloscope to measure the voltage versus time, and also the rotational speed of the rotors about the shaft was also recorded by using a tachometer. As you can see over here is a graph showing the voltage versus time that we sketched based on the data from recorded from the oscilloscope. As you can see, the peak voltage is about 0.3 volt, which is much lower than the expected, since our system is not fully functioning due to the wobble of the system and friction. However, we're still in the process of revising and testing. Our dynamic components consisted of motor, slip ring, and ball bearing costing about $32. However, the PLA material costed the most, which was about $35, knowing that our system was mostly 3D printed. In total, costing about $105. The conceptualization began on September 22nd, and then from there, we constructed our prototype on October 6th, and then for the following 8 weeks, we redeveloped, tested, and obtained results. That's the end of our presentation. Thank you so much for listening. Any questions?
The top half counter-rotating against the bottom half versus having everything rotate together. What was the purpose for that design decision?
So as the top half, as shown in the motion study, counter-rotates against the bottom half, the magnetic flux of the generator is increasing, and that's supposed to create more voltage compared to if the whole thing is spinning. Just the stator would be stationary and the rotor is spinning against each other. But now if they're spinning relative to each other, there's more voltage created.
Basically, you're getting twice the RPM
Exactly.
without a gearbox.
Yes.
Okay. And is the top half supported entirely by the motor shaft, or is there anything else supporting the top half of the structure there?
So yes, initially the top half was just solely supported by that, but we found that the motor that we got, the shaft was too small, so we built an external stand that attaches to the top of the turbine and holds that part in place.
Okay. Okay, thanks.
So let me ask a little bit about some of your experimental results and how it may have matched up with your modeling. You had mentioned, I think, that there was some friction and maybe some other error sources that may not have given you a good comparison. Could you allude a little more to, some of those details beside just friction?
I got it. So once, as I said earlier, there was initially wobble due to the top turbine being solely supported by that. And because of this, when the wind hits it, the whole system is tipping back and forth. And we also found that we printed the base at the beginning of our conceptualization, and over time it started to warp. So that also caused there to be an increase in the wobble because the ball bearing was not spinning freely and it was hitting part of the base. So because of that, it threw off the forces and caused an imbalance, and also the top turbine also was not spinning as it should. So sometimes they'll start to spin contrary to each other, but once there's that wobble and the friction with the base, it will slow down, and then one turbine would spin and both would spin in the same direction.
So from a mechanical aspect, what would you do differently given more time and or resources?
So we would get an output shaft that's much bigger that could better support the top turbine, and we were also creating that external fixture to help support the top turbine from wobbling. So that's what we actually recently finished that, and it improved it a lot. For the base, we would not use the material that we used, which is PLA plus because of warping, but we'll get something more stable, such as wood, to keep it uniform and flat.
And to add to that, we wish we were able to make the diameter, the radius or diameter of the Savonius blade a little bit bigger, so it can catch more wind when the wind hits the system.
All right, congratulations on your last presentation. And yeah, you can actually put this over there. All right. All right, our next team, softball. Come on out. And I think your client is here. There he is. I have an extra mic over here.
Yeah, we're ready. All right. Good morning, everyone. Welcome to our final presentation. We are Group 3 Catch and Return. I am Kyle Naughton. This is Thomas Yost, Jacob Moran, and Azana McQuanant. Our client is Assistant Athletic Director Kevin Gibbons O'Neill. He has tasked us with creating a device that allows the pitcher to practice independently from the rest of the team for the UMBC softball team. He has given us a used Pitcher Pocket Pro device to implement in our final design. So for our device, we developed a set of system requirements. We broke these down into a set of 3, which are performance, functionality, and safety. For functionality, we need to be able to move a 6-ounce ball back to the user. For performance, we want to be able to move multiple balls at a time without jamming and in a timely manner, and also have the equipment be able to be moved by 1 to 2 people. And for safety, we need to make sure that the electronics are properly grounded and waterproof, and that all moving parts are properly encased so that no hair or jewelry gets caught in it.
We broke the design up into 3 different sub-assemblies to better design our solution to this problem. The first sub-assembly is the funnel system, then we have the ball elevator, and finally the return pipe. The funnel system is made up of the donated Pitcher Pocket Pro, which we fit with a wooden funnel that sits inside the net so that when a pitcher throws a ball into the net, it'll roll down into the funnel and then roll off to the side to interface with the next system. The second system, the ball elevator, will then interface and grab the ball from the funnel. The ball elevator is going to be using a 3/8 inch pitch chain, a variable speed motor, and metal ball attachments, or chain attachments that will allow us to connect a wire ball grabber to the chain, which will grab from the funnel system and elevate the ball. Once the ball has reached the approximate 6-foot elevation we need it to, it'll then deposit it into the third system, which is the return pipe. The return pipe is going to be made up of 4-inch internal diameter PVC piping. This piping is going to be rigidly mounted to a fence next to the UMBC softball field. It's going to permanently stay there. It's going to be weatherproofed, and it'll be designed so that when the other two subsystems are put in alignment with this system, the device should function as expected. The most important aspect of our design here was the elevator. We thought if we could make that work, surely we could make this project work. So we spent a lot of time ensuring that that subsystem would function properly. We start out here on the left with a proof of concept, simply a motor 2-gear chain-driven system. Just to kind of get an idea across to our client that we were on the same page. This only offers vertical and no horizontal motion at this point. We then wanted to reduce the number of moving parts, and so we considered an Archimedes screw design. We were advised that this might be a little bit more trouble than it was worth, but we still designed out the full CAD model, but we heeded that advice when it came time to prototyping. We designed a third propulsion system to get that ball up, which was an air propulsion system. It worked very well at the small scale, but when talking with the client, we found out quickly that the the noise pollution the air propulsion system would be too great when we scaled it up to the size of the softball. We moved away from air propulsion. We then went back to the CAD model of the Archimedes screw. We prototyped one out fully, and we ran into some trouble there. Two main issues are that the softball has a very high grip. It's designed that way to be caught and thrown. And in addition, the laces on the ball make it so that it's not perfectly spherical. These two factors make it so that a softball is almost the perfect object to jam an Archimedes screw ball lift device. Therefore, we moved back towards another design.
So here we have our final design. On the left, we have the Pitcher Pocket Pro and funnel system. The funnel would sit inside of the net of the Pitcher Pocket Pro and also sit on the legs of the Pitcher Pocket Pro. And the ball would drop down into the funnel, move to the right towards a guide system that would hold the ball in place until the ball elevator could come and pick it up. And then on the right here, we have our ball elevator. It was designed to have be as lightweight as we could make it. We made it out with a wooden framing that would support the chain and sprocket a ball lift, and then we would attach chain attachments to the chain that would also have claws attached to them to come and pick up the ball from the guides. The system would be powered by a motor on the bottom, and on the bottom left side is the housing for it. We would also attach the speed controller and shut-off switch to that housing. So for our fabrication, we currently have the ball funnel completed. We made it out of plywood and wood fasteners so that it would be very lightweight because the Pitcher Pocket Pro is already fairly heavy. We wanted to make sure that they could move it in a timely manner. We also have the ball elevator partially completed. We have the main components of it done. We have the chain in place. We have the motor secured, and all the framing is done. So far, we only need to really complete the safety aspects of it, of getting the cover on the for the chain and sprocket so that no one can get anything caught in it. For the return pipe, we had some issues getting our motor in, which would complete the ball elevator. And with the ball elevator needing to be at a certain height, we had to be careful that the return pipe was in the correct place. So we wanted to complete it and get that all situated. So we haven't assembled that yet. We are planning to do that very soon. as the motor only came in recently. So we did do some testing to make sure that we could get an appropriate slope. We tested a 20-foot length. We have a total of 40 feet that we need to achieve. And so we did that to get some progress on that system.
Next, for our project, we had to make sure that testing was done after fabrication was completed. We wanted to make sure that the functional, performance, and safety requirements were all checked off. For our funnel system, we wanted to make sure that the ramp slope was appropriate and led to the appropriate place for the ball hands so that it could be hooked up by the ball elevator. To do this, we simply just tested how multiple balls would interact with that, roll down and sit in the appropriate location, and made adjustments as we went along. For our ball elevator, we had to make sure it was able to lift it to the appropriate height. To test this, we simply let the system run at first and see how the balls would interact with it and made adjustments to the chain strength and slack to make sure it was able to lift it up. Basically, we saw how that worked at first and then saw how it interacted with the funnel, seeing that the ball was able to be scooped up and dropped off into the return chute, which was appropriate. We wanted to make sure that our motor was also able to shut off if necessary at any time, so we had to test a shut-off switch. And lastly, for our PVC pipe return chute, we had to make sure that the internal diameter was appropriate to allow the ball to move all the way back to the pitcher. And we did this by just simply putting the ball inside, seeing how it interacted, and determining the appropriate slope. Next, we have our budget. We spent a total of $723, with the bulk of it coming from the PVC pipe, electric motor, and sprockets and shafts from McMaster-Carr. And then lastly, for our timeline, we thought of our initial concept in the beginning of October. Next, we completed prototyping in the beginning of November, and a week later, we decided on our final design. Going forward, we're going to finish the assembly on Monday, the 11th, finish testing and making adjustments on the 13th, and have our final client demo on the 15th. Thank you. Any questions?
How did you choose the motor and the chain and the sprocket, the sizing and ratings for those?
So when we decided to choose our parts, for the size, we mostly wanted to go with as lightweight as possible, so we didn't want anything super big. We also were having some size constraints because we didn't want to have insanely heavy, like 2x12 boards supporting the structure. So we wanted to keep it within the about 5.5 inches for the framing. And then the chain we chose because we could find some chain attachments very easily on McMaster-Carr. And then for the motor, we did some analysis on what the total torque we would need for the system. The balls are fairly lightweight. The chain was about 2 pounds total, so it wasn't insanely heavy. So we mostly were looking for variable speed for our motors. So the motor's total torque is about 16 Newton meters. That is much more than we probably needed.
Okay. Thank you.
To go along that question that was asked earlier, my question is also around the engineer analysis. Did you do any force calculations to see, okay, how much force you would be expecting when you're trying to catch the ball, when it's shot from a player or you're trying to catch it, how much force is going to be generated when it comes to receiving, and then how much force you also need to go when it comes to returning the ball back to where it's supposed to go? Did you do any calculations on that? And can you explain how you came about deciding, okay, how do you want to size your equipment to make sure that it withstands those forces and also able to meet the estimations, right? So how far are you trying to return the ball, right? What is the maximum force you're expecting to receive if a player shoots the ball and then you catch it? Can anyone elaborate on that?
Yeah, so some of the part selection was based around two things of keeping it as cheap as possible and as light as possible. For example, the PVC piping, we have 4-inch internal diameter. The softball is 3.8 inches, and we did a lot of testing to make sure that would be big enough to still achieve like a return pipe that we wanted to without making it overly large, overly costly, overly heavy. In addition, in terms of the return chute specifically, we did do some calculations, but we found the best approach to determining if that was going to work was physically holding these pipes up against a fence or a wall and rolling the ball down to see what gradient, what height differential we could achieve. And we found that about a 1.5 foot over 10-foot drop is probably pretty guaranteed to get the ball to roll down the other end. As for the forces of the pitcher going to the net, luckily we were given a market available product, the Pitcher Pocket Pro, which is designed to withstand these speeds, but we did do some research into the typical average college-age softball pitcher, and they could produce speeds, I believe, up to around 65 miles per hour. So it is a very fast ball coming in the back of that net, and that's something we're going to have to continue to test for and try to make improvements to. But we are very fortunate that we were donated this device that essentially is designed to catch balls that speed or faster. So having that was a huge advantage.
You mentioned the noise of the motor being an issue with one of your design iterations, and coming back to this one, can you speak at all to any other feedback from the end users and how that informed your design?
You said feedback from what?
From your end users, right? The pitchers or the team, they're going to want to make sure that this works well for them. How, in your analysis or research or discussions with them, has any of that informed other elements of your design?
Right, so one thing that was a really early on important aspect of the design was the height of the Pitcher Pocket Pro. Apparently we found out that when they use this at practice, they usually leave it at the fully downward position. It's actually adjustable height. You can bring it up. I don't believe that's actually where the legal batter box would sit, not all the way at the ground, mind you, but they just kind of did that for ease of mobility. We therefore tried to get the approximate location of the batter box that they would be using, and then built the funnel system off of that height, knowing exactly where we needed to rigidly lock the Pitcher Pocket Pro in at. Besides that, we generally went with common sense after the air propulsion situation. We realized that even at, getting a metal ball bearing to go up the elevator, we were like, this is already noisy. We're going to use leaf blowers or something even louder, and that's going to disrupt all of practice. So a little bit of each, I'd say.
Thank you.
Congratulations on your last presentation. Can we give him a round of applause? All right, and our next team, you want to come on out, which is our Baltimore Gas and Electric group. And I have a microphone over here. And please make sure, again, you hold your mic to your mouth.
All right, good morning, everybody. This is our presentation on our copper pipe removal tool. I'm Brandon, this is John. On your left is Daniel, and on the right is Andrew. And we've been working with BGE's gas division. So right into the background, basically in the mid to late 1800s, BGE started burying steel gas lines in the ground to deliver natural gas to homes. And what happens when you bury unprotected steel in the ground is it starts to rust away and corrode. So in order to keep these lines in service, inside of the larger steel pipe, they inserted smaller copper pipe as liners to keep them in service. And basically the problem that they're having now is that they would like to remove these copper pipes and reinstall plastic liners instead, but still inside of the steel liner. So what they needed to do is they need to find a way to remove the copper pipe while keeping the existing steel pipe in place so that they can reinstall the plastic. And they've been trying to find a tool to do this, and they haven't been able to find one, so that's where we come in.
So some of the systems requirements were given to us by BGE, and some of them we came up with ourselves. BGE told us that they wanted this tool to be compatible with the Takeuchi TB240 excavator, which they frequently use for these jobs. They wanted the tool to function without the crew being inside the hole they dug for safety purposes. We determined that the tool should be able to withstand 5,000 pounds of pulling force because the excavator can theoretically pull up to 4,100 pounds. And 10,000 pounds of compression force because the cylinder we chose can withstand up to 3,000 psi, which translates to roughly 9,000 pounds of compression force. We wanted the tool to be compact in order to fit within the hole easily, as well as on the trucks. And then we wanted the tool to withstand the wet and muddy conditions that it would be experiencing on job sites. And then lastly, we wanted the tool to be entirely mechanical in order to save cost and make the product simple to maintain.
All right, so the design of our tool involves a custom excavator attachment that, that includes a small hydraulic cylinder that will be plumbed into the excavator boom auxiliary hydraulics, and this hydraulic cylinder will be used to crush and clamp the pipe to pull out of the hole. So as you can see here, they're going to dig a hole, they're going to remove the steel liner, they're going to line our excavator attachment with the copper pipe. The operator will then activate the hydraulics, clamping the copper pipe, and then he could just pull the boom back and pulling the copper out of the hole. He can then uncompress the cylinder, releasing the copper. He'll then advance the tool and repeat the cycle, clamp, pull, unclamp, advance, clamp, pull, etc., until the roughly 30 to 80 foot stretch of soft copper pipe is out of the hole.
To go over our prototypes throughout the semester, in that animation, that was our first prototype. The difference between the first one and the second one, we had received a connection bracket, which is on the top, from BG&E, so we had to alter our design a little. That included the top and the bottom, widening the bases there. And then the difference between the second and the third prototype is BG&E recommended that we move up the cylinder from the rear of the tool to the middle, and then we also added safety flaps on the far right image there.
So the actual clamping jaws of our tool, we initially had more of a serrated jaw design, but we were concerned about, during compression, shearing the copper itself. So at the recommendation of our professor, Dr. Von Lockett, we went with more of a smooth, wavy design, so to limit the chance of shearing the pipe during compression, but also increasing the mechanical coupling rather than just flat blocks of steel. And those jaws are CNC cut out of just standard soft 1018 steel. We didn't feel we need to harden them because it's substantial, and they may down the road, and those are user replaceable, just bolting in.
So moving on to the aspects of safety and also the analysis that we've done with the tool. As we mentioned previously with the final prototype, we added rubber safety flaps at the recommendation of BGE to the front opening where the copper pipe goes in. This is just to make sure that nobody is putting fingers where they're not supposed to go. We also did a finite element analysis for the frame because, as mentioned earlier, the hydraulic cylinder can exert almost like 9,000 pounds of compression on the tool, and also the excavator can pull with about 4,000 pounds. So we just simulated those loads in SolidWorks. This is only for the frame. That's the only part that we looked at for the finite element analysis. The tool's about 2 feet tall and about 1 foot wide, so those plates on the side are pretty flat, and we just wanted to make sure that they were strong enough, and the factor of safety there was like well over 5. And then by hand, we did an analysis where the bolts attached the top mounting bracket to the rest of the frame, just to make sure that those weren't going to damage the steel. For the copper pipe, where it's being compressed in the jaws and the tension is being applied as you pull it out of the ground, we did more circle on that to make sure it wasn't going to fracture. And then we also looked at the strain on the copper pipe as a result of the wavy jaw design, and all of those calculations checked out, and we're happy with the performance of the tool.
All right, so for the fabrication itself, we were lucky that BG&E had a CNC fiber laser on site, so they were able to very accurately cut out our 3/8 inch plate steel, and we included tab and slots for alignment. They then took the side panels, and they had a big hydraulic press brake, and they bent those into shape, and they got that all slotted together, and then Brian the welder tacked everything up, and then went back with a stick welder to get really good penetration on all the necessary joints.
After our fabrication, we moved into the final product assembly, and that involved painting the tool, which, as you can see, it is our gas meter gray. In the far left, you can see how the cylinder is bolted in and attached with the hydraulic hoses. In the middle, you can see the safety flaps guarding the jaw where it compresses the pipe, and then the far right image is just what it looks like behind the safety flap.
So for some quick testing, we haven't done our complete round of testing yet. This is, we actually did this yesterday. This is just some quick performance testing. So we hooked up the tool to the excavator. We wanted to make sure everything was working properly. The hydraulic cylinder works. It was able to compress the pipe. And BGE basically just took a piece of copper pipe and just put a bunch of gravel on top of it and parked a big giant dump truck on top to make sure there was some resistance there. But this is not the full round of testing. We do want to test later with like water and mud on the pipe and everything for our full analysis, but you can play the clip real fast. And basically, he just lined it up with the tool. You can see he just activated the cylinder, and then he can just use the boom of the excavator to pull the pipe back. And they pulled out about 20 feet, and everybody seemed pretty happy with how it worked.
To quickly go over our budget, on the left side of the screen, we have what was provided by BG&E. That was mainly the hydraulic cylinder, the bucket connection, as well as the hydraulic hoses, and the CNCing of the steel jaw. And then on the right is what we were able to buy with our class project, and that was mainly just the hardware as well as the rubber safety flaps.
Here's a broad overview of our timeline. In the first 3 weeks, we focused on understanding what BGE wanted and how the tool would function. In the second part of our project, we focused on coming up with a conceptual design. We then worked on 2 prototypes, which we presented and got feedback on. We then came up with a final design based on our feedback, and then we've just completed some of our initial testing on it. Thank you all for coming and listening to our presentation. Does anyone have any questions?
Yeah, just any considerations for the maximum length of pipe that you guys can pull out without it interfering with the work going on around it, or ways to redirect the pipe so it is not coming right back at the operator and or interfering with the boom or any of the hydraulics as the length increases? I know you guys said 30 feet, but realistically, is there a maximum that they can do before they have to cut and reset, or is there any considerations for shifting the pipe away from the operator?
Yeah, so the copper, it's not hard copper, it's like a soft coil copper. So when they're only gonna pull out maybe like 4 or 5 feet at a time, however much the boom can swing. So they'll do one stroke, and as soon as it gets up towards the cab, another operator outside the hole can just direct it away. It's flexible enough, they can just push it away, and then they can just continue pulling. It'll just, and then another operator can just coil it up, basically. So, and if they want to, they can cut it at any point. But yeah, that wasn't really an issue, just because of how flexible the pipe is.
Yeah, so I'll add that a little bit. Well, when we did the testing yesterday, basically, like where the jaws actually crush the copper, it's like, at that point, it's very flimsy. You can like bend it with your hands. So what actually, like as they pulled the copper out, a guy just went behind the excavator and basically just like folded it over itself into like a nice little neat pile. Yeah, like an accordion.
I've got a question. So did you do any kind of analysis on the force, the clamping force, to maximize what that, or to optimize what that force would be?
Yeah, so there was a lot of, basically the biggest concern that we had is, you know, how much force you want to clamp basically is how much friction do you need to not have it slip out of the jaws. And basically, long story short, the coefficient of friction between copper and steel is give or take about 0.5. And we know that the boom arm of the excavator can pull with a maximum of about 4,100 pounds. So our cylinder can compress with 9,000 pounds. So just going straight off like napkin math, if we compress with 9,000, coefficient of friction is 0.5. That's 4,500 pounds, which is already more than the excavator can pull with. So that was our first thing. And then we also implemented the wavy jaw design just to make sure, because of course, if there's like water or mud on the pipe, that would decrease our coefficient of friction, which we plan to test later. And then just like going off of what BGE has told us, they haven't had problems really with the pipe not like tearing or anything or not being able to pull. So
is there, are you going to put any kind of sensors inside so you actually have feedback on what that force is, or?
We were not planning on doing that.
So not a sensor, but the newer excavators that they're using, it'll give a readout of what the hydraulic pressure is currently on the auxiliary hydraulics, so they can set it to whatever they want. So if they set it to 3,000, which is the maximum, we know just based on the 2-inch bore cylinder how much force it's going to apply. And then if for some reason, if it's like breaking the pipe or whatever, they can decrease it to 75% pressure and apply less force. So they have a digital readout in the cab, but it's not like an active pressure gauge or anything, but it's more just set it and go from there.
Thank you.
Mm-hmm.
And we have a question online from Eris from College Park. Will this tool be used to insert the new PVC pipe linear as well? If so, have you considered how to prevent crushing the PVC pipe during the gripping process?
It will not. This is just purely removal. They have already, I guess, assume a method to insert the the plastic. This is purely just removal because that's the main issue that they're having is removing the copper pipe.
Congratulations on your final presentation. Thank you very much. And our next group can come on out. This is our airfoil control system group.
Good morning, everyone. We are Team AeroNexus, and thank you for attending our final product presentation on the AeroFlex system. Our team consists of Tamia Bowers, Daniel Quinn, Joe Yartel, and myself, Yasin Drame. Our clients are Emily Cruzon and her PhD advisor, Dr. Charles Eggleton. Our client is trying to find the best angle of attack that will increase lift yet reduce drag. She's using an Aerolab wind tunnel, a 3D printed airfoil, and a photo image velocimetry system. Currently, the client is using a protractor to find the best angle per test. However, this leads to a lot of inaccurate measurements and is troublesome for the client. Our goal is to create a device that will accurately and conveniently change the angle of attack. We had many system requirements for this project. However, the most important one is to make sure that the device changes the angle within 0.1 degrees of tolerance.
We've adapted to an agile methodological approach in which our team started by conceptualizing design ideas. We moved forward by developing upon them through written documentation, sketches, and team working meetings. And once we were able to develop a prototype, we validated that the device completed the testing stage through operational and functional integrity testing, and finishing off with a retrospective or an evaluative meeting to ensure that we've met our desired goal. We functionally broke down our product production into 3 stages, the first being mechanical components, where we developed the frame and the body of our device, moving to the electrical components, where we utilize evaluative methods to select the electronics for our device, such as the stepper motor and the stepper motor driver, and lastly, the control system, where we evaluated the interconnected aspects and functionality of the electronics, and we developed upon the user interface.
So here's the timeline for what would become the AeroFlex device. Our chosen idea from the ideation stage was simulated via CAD modeling for prototype 1. Further development of this was done for prototype 2, as well as the physical frame being assembled, and looking at the top left image, a simulation of the user input of the LCD with 2 isolated buttons. From this to what would become the final product, we changed from the keypad and LCD to an LCD shield. Programming was done, as well as the final components being assembled, and then testing was done, which verified that our device was a functional product that satisfied clients' requests. Our budget followed the timeline in 3 different phases. Phase 1 included materials for the physical frame. Phase 2 included the electrical component, and Phase 3 for safety and final touches. In total, we spent a total of $467.
Now, from ideation to prototyping and development, we would now like to feature the AeroFlex system, an actuation device capable of moving 1/10 of a degree for accurate testing of the angle of attack airfoil within Emily's experiment. Now, with this system, what we have outlined here is essentially just the main components that go into our product. I do want to highlight a couple of our key features, starting with the NEMA 23 2-phase stepper motor, in which we selected due to its ample holding torque that would allow for us to hold the airfoil within the wind tunnel during testing, which we've decreased the step angle from 1.8 degrees or 200 pulses per revolution to 25,600 pulses per revolution in order to get as precise as possible to the 0.1 increments that we need for testing. Here we have our user interface, which we designed user-centered intuitively, in which the user is able to increment and decrement by degrees of 1 and 0.1 simply by selecting those buttons there, toggling between the buttons, and they're able to enter their desired angle of attack.
So to house all of our electronic components, as well as mount the device to the wind tunnel, we chose to use the 80/20 aluminum T-slot building system. What you can see in the upper left is that aluminum extrusion. We also used various 90-degree brackets from the same company to attach all those extrusions together, and then the miscellaneous hardware required, which was T-slot nuts, machine screws, and washers. Additionally, we had a high-density polyethylene sheet laser cut to size to mount all of the electronic components, which was mounted to the frame. On the left side, you can see the assembled frame with those aluminum extrusions cut to length using a dry cut chop saw, which allowed the lengths to be very accurate, so the frame was the expected dimensions and fit on the wind tunnel as we expected. Of course, the 80/20 system is adjustable, so if we needed to, we could adjust it to make it fit even better. On the right side, within the red circle, you can see a small aluminum block. What that does is adapts the 4-hole mounting pattern for the toggle clamp to the 2-hole pattern that is needed to mount it to the aluminum extrusion. So you can see in the upper left image, the HDPE sheets have been mounted to the frame. Once that was done, the electronic component mounting patterns were found in their respective data sheets, drilled in those HDPE sheets, and then the components could be mounted. Once they were all secured and held in place, we then wired them together with strain relief in mind, especially the 120-volt AC power cord that leaves the device. Because the user will be handling that, it moves around a lot, so strain relief is extra important for that one. Additionally, the Arduino is currently mounted using 3M VHB, which stands for very high bond, so it's very secure right now, but we think we can do better, so we're going to 3D print an enclosure for the Arduino and attach it using hardware. So for some of those more basic system requirements, we had an initial testing plan for temperature, which was over a 12-hour period to be sure that the device, any components on the device don't exceed a temperature that we expected when the client is using the device. And then physical testing, of course, fit and finish, making sure it fits on the wind tunnel, sharp edges for safety, and shocking hazards. So the most important system requirement was that precision, 0.1 degrees. That involves some interesting testing. The Imaging Research Center right here on campus helped us do this. What we did was take some high-resolution images of the airfoil at different angles, starting from 0 degrees, 1/10 of a degree, 1/2 a degree, and then 1 degree. Those images were then loaded into image processing software, where we could take actual measurements of what the airfoil actually did. So the result of that is the motor rotated 0.0991 degrees when we told it to rotate 1/10 of a degree. That's a difference of 9/10,000ths of a degree, or 0.9% error, which is excellent. And then for those other system requirements, the temperature, we found it, the stepper motor was the hottest device, and that reached 117 degrees, which is barely above warm, so there's no danger there. Physical testing, it fit very rigid, as you can see in the bottom video there. All the edges were made sure there was no burrs or any sharp edges. The shocking hazard will need to be addressed because that power supply has some exposed terminals where the 120-volt power cord attaches to it. So to address that, we're just going to 3D print a cover that will cover those terminals. And that's all we have for you. So any questions?
Thank you. I appreciate the consideration for, putting together a package like this. You did mention something about your accuracy. And my first question as you were going through this was mounting accuracy. So in other words, how do you know when 0 is 0? There's an increment as you've prescribed, and I know you mentioned there's an error there. I'd like you to offer a reason to why there's an error between the increments of what you prescribed and what you actually saw. And then I'm also going to ask about how you can mount it and make sure that 0 is 0.
Yeah, so we did consider that. As far as accuracy, which is kind of if you can hit the spot that you're actually aiming for, every time the device is mounted to the wind tunnel, there's a calibration procedure which will be zeroing it out that the user will have to do. And like I said, it's very rigid on the wind tunnel, so it won't be moving during the test. And then as far as precision with that slight change, when we tell it to move 1/10 of a degree, the reason it doesn't hit that exactly is because there's inertia in the stator and static friction, different factors that might change it a little bit. But like I said, that precision value is really close to what we need. The user will actually only be testing to a half a degree, so a tenth of a degree we believe is far below that and should be good enough for testing.
Did you perform any analysis to determine how the actual wind load might affect the precision of the angle of attack?
So we did perform some analysis in a worst case scenario. We figured the airfoil only goes to 12 degrees when in the user's testing. We put it at 90 degrees exact against wind flow, and the user is only going up to 5 meters per second. We set a multiple of that. We tried 10, 15. So that was a very worst case scenario. We still had plenty of torque to hold it in that case. And that's actually how we chose our stepper motor size, which is its holding torque. And then once we received the stepper motor and built the device, we did kind of a heuristic testing where we tried to move it by hand, and we couldn't even move it by hand. So we have plenty of torque to hold the airfoil.
Okay, so that's certainly one component of it would be not overcoming the holding power of the motor, right? Another component might be the rigidity of the whole assembly, how that rigidity reacts to the force of the wind load. Did you consider that?
We considered it. We haven't done testing, like FEA testing.
Okay.
We can do that in the future, but based on, like I said, heuristic testing, the device is extremely rigid and the wind speeds aren't very high, so we're pretty sure that it's going to be strong enough.
Thanks.
Mm-hmm.
How are you securing the airfoil and attaching the airfoil to the stepper motor? And the reason I'm asking that question is there any concern over time that that connection, there could be potential slip, which the motor itself and your measuring device can show that, okay, the shaft is at 0 degrees, but because of slippage between that connection between the foil and the shaft of the motor, over time, the airfoil itself is not at 0 degrees anymore?
That's an excellent question. We actually considered that by using an encoder on the shaft. We didn't do that because it would add an extra level of complexity that we didn't think we needed yet. In the future, we could add that. Right now, the airfoil is on 2 axles out of each end of the airfoil, and on each side of the wind tunnel, there's a plexiglass window with a bushing and a hole in a bushing that the axles go through. So that is what's supporting the airfoil, and then the only thing that the stepper motor is doing is attached to one of those shafts using a shaft coupler. And it has a set screw, and we'll have it's a D-slot shaft, or it has a flat spot on the shaft that the set screw pushes against, so it's pretty much impossible for it to rotate unexpectedly.
Okay.
And your client is here in the audience, so I'd say thank you very much. You proud? You good? Thank you. All right. All right, congratulations on your final presentation. And I will remind also that we have lots of users online, by the way, and they're leaving some very lovely comments to all of you as well. So our next team is our next BG&E group dealing with UAV. And let Emily know when you're ready.
Yeah, you're kind of.
Yeah, we're ready. Okay, cool. Yeah. All right. Hello, everyone. We are Grid Guard. My name is Andrew. This is Alex. Yes, sir. And Kendall. So, it's not. Yeah, the first slide. Yeah, it's the red button. Okay. So that's better, yeah. So we work with BGE, specifically Clancy Richardson, and the problem that we had was that BGE had these power lines, and sometimes debris such as bird nests and tree branches would fall on them. And because of that, we were expected to make a drone attachment that would remotely place insulation on the power lines. So this attachment was very, very important. So one thing that was very important about it is that it could not affect the drone's capabilities And also, because these are energized power lines, the insulation couldn't be conductive, and also it couldn't exceed 6 pounds.
For our first prototype, we focused on designing the two major subsystems, the claw on the left and the winch on the right, to be made out of ABS plastic to meet the non-conductive requirement. For our second prototype, we redesigned the claw to make it simpler and have a pinch mechanism, and it houses a motor on the top connected to a threaded shaft that would open and close the claw, and on the right is an updated winch.
What you're seeing here is a 3D printed model of our second prototype for the winch. The purpose of this was to test out the functionality of the 3/8 grooving to house the 3/8 cable. As you can see, it's bolted to the ceiling of my basement. It ended up working pretty well. In the middle, we have a 10-pound weight suspended on the cable assembly, demonstrating that it could hold a weight that is almost twice the max weight of the entire assembly. And on the right, we have a video of the cable unspooling. Here is the final design. We have a DC motor driving gears. The DC motor goes into a gearbox with a worm drive gear, which provides an increase of torque, but also locks the assembly so that the operator can choose how much cable they'd like to have dispensed. In the top right corner is a slip ring, because unlike traditional winches, this is going to be designed to have electrical signals so that you could use an electric claw or have extra attachments. Below that is a CAD model of the 3/8 nylon tube. It's going to house 3 17-gauge cables, which is going to allow us to transmit 1.5 amps over a distance of 9 feet without any voltage drop.
Our latest solution for our claw was purchased via a third party, and to still meet the requirement for non-conductive materials, we are going to put shrink wrap insulation over it. And in the middle, you can see a CAD model of this claw, and it has a max clamping force of 1.5 pounds. And on the right was the tube with the coupler that will be attached to the top of the claw.
The last piece of the puzzle with this project is getting the electronics to integrate with the drone. DJI provides a payload development kit that allows us to utilize their proprietary interface called Skyport. It is the circular interface that provides a 24-volt connection as well as a data transmission. It breaks out to this black PCB board, which has Ethernet capabilities as well as voltage. However, the voltage that the development board gives out is not great for applications, so we have a few DC to DC converters to get 7.4 volts for the claw, 5 volts for the Raspberry Pi, and 12 volts for the winch motor. The Raspberry Pi is going to connect to a serial converter in order to establish a connection with the DJI Skyport interface. And also we have a H driver to control the speed and direction of the winch motor. To the right, we have an in-depth picture of the nylon tubing with a 17-gauge wire.
This is the first FEA of the winch subsystem. This is made entirely of ABS plastic, and it was tested with 12 pounds, which is double the expected weight for it. Now, the yield strength for ABS is double the magnitude of anything this would experience as measured in SolidWorks. This is the FEA for the control board, which will house the Skyport, Raspberry Pi, and various other electronics. This was also fully ABS plastic, tested at 12 pounds again, and the yield strength is 1 order of magnitude higher than anything it would experience. As shown here is a full CAD model of our system attached to the DJI drone. Just a visual with the claw winch system. This is a breakdown of the component weight. The total of everything is 3.46 pounds, as well as an additional 1.5 pounds for whichever insulation payload BGE decides to use. This is a breakdown of our budget for the prototyping components, as well as the electronics from the DJI Skyport and the Raspberry Pi. And in the next part is for the mechanical components purchased. This is a total of $531.58 with various other miscellaneous parts.
So for the testing we've done so far, like Esru spoke on, we did the FEA for the winch, the bracket, and for the control board. And we also did cable strength testing. And one thing that was kind of important is that the maximum strength that was necessary was 6 pounds, but we were able to get the cable to be 25 pounds, so we tested it really well. The future testing we have, is so we have to test the claw, winch, and the control board with the skyport, because that's basically the brain of the drone. And speaking on a little bit of this, so the final things we have to do are the final assembly, which is putting everything together, scheduling our demo, and making our final report. And that will complete our project. Any questions?
So do you have a drone to test with?
So what did you say?
Do you have a drone to test with?
Yes, okay. So the drone is only at BGE. It's a $10,000 drone, so we're not really allowed to access to it at every point in time. But because of that, we're going to be going to BGE very soon to test the drone with all the attachments that we made with the skyport as well.
Okay.
Thanks.
So real quick, I think you said 6 pounds was the maximum weight that you could add to the structure or the UAV?
No, so 6 pounds was the required. So 6 pounds was basically what you were saying, which is how heavy the drone could carry.
Could carry.
Yeah.
And what are you supposed to carry? So you have a claw, you have a mechanism that opens and closes. I thought initially you were talking about putting something over, like some kind of insulation. How much will that weigh? Like, I'm curious as to what you need to carry versus what parasitic mass you've added to the UAV, or is that not an issue?
Yeah, so the system entirely weighs 3.5 pounds, and the claw we went with has a max clamping force of 1.5 pounds. However, we have purchased a higher strength servo motor to get this up to 3 pounds. BG&E has other types of drones that could hold up to 13 pounds. This is a DJI Matrix 300 RTK. It could only do 6 pounds, so the winch assembly is kind of heavy. For this to be used in practice, I'd recommend that they use their larger drone with the 13-pound capacity.
And what we will be picking up with the claw would be insulation material that would be placed onto the energized wires. That's to answer that question.
And do you have an approximate weight for that insulation material?
There's different insulation materials that they already have and used, and they have blankets that are really, really heavy, but we would have to cut them down to be able to use it with our system. But there's also like other insulation material, but it's in like the 2 to 3 pound range, so.
To add on to what he said, we can't modify the insulation at all. It has to meet up to all of BGE's requirements. So anything they use would be made by them.
Thank you.
You talked a little bit about the shrink wrap to insulate the jaws. Have you tested that yet, or applied the shrink wrap?
We have not tested that yet.
We have it purchased, and we could show it to you at the table. It's a 70 millimeter shrink wrap, 2-to-1, so it should be 35. The drone is about 53 millimeters in that dimension, so it should be more than sufficient, just to cover up like the fasteners and the one metal plate and the 3/8 compression fitting.
Okay, thank you.
And do you have any limitations on the type of installation material that BG will be using this for? I know you mentioned it could be different things, but do you know those to know that, okay, your clamping mechanism is going to be able to carry those items securely?
BG&E simply wanted us to create a system that could be used to place their installation. The claw that we purchased, only 1.5 pounds. So later down the road with future testing, upgraded servos, we can get it higher. We don't want to modify any insulation, especially dealing with power lines. We could see upwards of a couple thousand volts, just to be on the safe side.
Yeah, the question was more so on, do you know that the clamping is going to be able to hold on to whatever that installation material is? Sounds like you're not sure exactly what that material could be, and it could be anything. Do you know that the clamp that you're using is always going to be able to pick up whatever they're trying to pick up, or are there any limitations?
Yeah, so the limitations would be up to the installation they use. We have no control over what type of installation, as if we were to modify it, cut it, or reduce the weight, it would invalidate any type of standards they have for that installation. So they would ideally use one that they have that would work with our system, or develop a new installation that could be placed in accordance with the drone. Because right now their solution is to have a person go up and place it by hand.
Okay.
Congratulations on your last presentation. All right, our next group is our volunteer medical engineers group.
Hi, thank you for joining us today. We are Team 7. My name's Alyssa. This is Chris. We have Ethan and Tim, and we worked with the Volunteer of Medical Engineers. This is our final presentation on Kage's wheelchair tray. So for a brief project scope, we are designing a wheelchair tray attachment so that Kage can interact with his toys in a safe and effective way. Moving on for some requirements, we want a one-size-fits-all so that he can have numerous tray attachments on his tray at once, and it needs to be compatible with his wheelchair. For some customer information, we have Kage, who's a 3-year-old boy with microcephaly. He has cognitive and developmental delays, and he is at Kennedy Krieger Institute, where we are working with his physical therapists, Temra and Mira. These are some photos of Kage and a brief video that shows how he interacts with basically any toy. It shows a beanbag, but he will throw just about anything. So ideally, we want to find a way to secure these toys to his wheelchair tray.
So here you can see CAD models of our initial design. Initially, we wanted to go with a pegboard tray where each of the attachments would have matching pegs, and all the attachments would be able to place easily anywhere on the tray. While we liked the convenience of this design, we didn't like the idea of having holes all over the surface of the tray, and we felt that with the size that the holes would have to be, Kage could easily end up getting his hands caught in the holes and pose a safety concern. Our next design, we had the idea of these rubber grips that would collapse around the base of any of his toys. With this design, we would be limited to placing toys only on the front edge of the tray, and we felt a simpler design was necessary. Our next prototype, our prototype 1, you can see on the right, we had these 4 corner holding pieces. These corner pieces would be able to raise and lower depending on the height of the toys. They would be connected to the tray using suction cups. Our second attachment you can see on the left, it would be located on the far end of the tray and would use a retractable ID badge reel or a retractable leash. This would be able to hold on to any of his toys that he plays with. He plays with these balls or these toy plastic keys that he has and prevent him from throwing them from the tray and basically keep them on the tray. Our second prototype uses a tray provided us by Kage's physical therapist. It uses these locking suction cups to move the holding system anywhere on the tray easily. We decided not to go with the retractable reel system because we figured that its performance would be a little unpredictable, and we felt that the toys could fly back in Kage's face, or the cord could wrap around his arm and pose a safety concern like that. Instead, you can see on the right, we decided to go with a bungee safety strap connected to one of our suction cups. This would allow us to keep the toys on the tray a little more safely. Our holding system is made up of a modified C-clamp and a 3D printed connector piece. The connector piece would connect the C-clamp to the suction cup, and we're planning on having 6 of these holding systems and 2 of the bungee systems connected to our suction cups. Once we decided which suction cups we wanted to use, we did force calculations to determine how much force would actually be required to remove these suction cups from the tray. Assuming a near-perfect suction is created between the suction cups and the surface of the tray, we found that about 92 pounds of force is required to remove the suction cups from the tray.
So next, coming in from our calculations we went to the engineering room and we started testing on these. So we tested the suction cups specifically right on the edge, but we didn't test higher. But we used force gauges, 2 force gauges that go from 10 newtons to 50 newtons, and pulled on both of these, creating a 100 Newton force, which is 22.5 pounds. We determined that this would be adequate enough based on studies from Department of Trade and Industry doing tests on child safety, and figured this would be the size for a 5-year-old child. Kage's 3 at this time, but he's going to be growing with this progression system with the suction cups to use different toys. But we succeeded in all these tests, and definitely going to focus on pulling with more force until the suction cups break in the future. Next, moving into some of the materials, we use plexiglass. This is perfect for the suction cups. It's a non-porous material, and instead of wood like his previous chair, plexiglass would be perfect and be able to wash off materials and different stuff like food. And this was definitely a concern from the physical therapist as well. Next, with the toy holder bungee system, these are silicone safety straps. With all these materials, we made sure they were within ASTM standards, which we have a long list of them. Then we moved into our toy suction cup stand. We made sure the suction cups were good. We made sure they were a cheaper material, well, not cheaper, but a satisfiable material for them that they could repurchase later down the line. We also did the 3D printed connectors at different heights, so from 1.5 inches to 3.5 inches, and then the smaller pieces being from 1.5 down to the bottom of his tray. And then the modified C-clamps, we put a different friction of a material covering the metal pieces that he could be in contact with. And finally, we had a buckle to wrap around the back of the wheelchair to ensure it didn't come off when he's going to be using it.
So for the budget, we had a budget of $700, $500 from VME and $200 from UMBC. This is our cost list. This is everything that we bought and used. And the total came out to be around $340. And this is our final design. On the left, you can see our CAD model for it. And on the right, that is our suction cup system. It uses a 3D printed part to attach the suction cups to the modified C-clamp. And for our final timeline, we have various meetings with VME, but we also need to do some more testing and install the U-brackets underneath the tray. The U-brackets serve to prevent Kage from moving the tray much and prevent it from slipping off as well. We also need to meet with Kage one last time to give him the tray as well. And that's about it. Thank you very much. Is there any questions?
As a father of young children, I appreciate this presentation and the system you've come up with here. Does he use the tray for other things as well, like eating? I'm thinking about like foodstuffs or something that's going to cause an issue between your suction cups and the tray. Did you consider that? And if so, what are your thoughts there?
Yes, so ideally, originally they told us that they want something that can be a flat tray so that he can do eating or schoolwork or anything along those lines on the tray. But then they also wanted a way to be able to stabilize the toys when it is time for him to play with those toys. So they are going to have to be 2 separate. He's not going to, if he's got food and water all over his tray, that's going to have to be cleaned up before it can become time to put the toys on the tray. But they did want something that was universal, and he could have the toys on, toys could come off, and it could be a flat tray for just daily routine.
Great. And one quick follow-up on the clamps that you have to keep something onto the tray. Can you talk a little bit more about your design decisions there with respect to his access to the toy being potentially limited by the clamps?
So ideally, any toy that we'd be holding onto the tray, we'd be using the clamps connected facing further away from the toy or on the far edge. Like, we wouldn't use more than like 2 clamps for any toy to hold anything. So the toy would be like the main focus in the front.
Okay, thank you.
Have you had a chance to mount the tray to the chair yet, or is that's upcoming?
That is upcoming. We have been able to test the U-brackets that are going on the bottom of the tray to the wheelchair, and those are going to be going onto the wheelchair tray a little bit later.
Okay, thanks.
With the consideration of the suction cup as the holding feature to the tray, obviously you did talk about cleaning the surface and things like that, but I guess I wonder, are there any aging of the material, of the rubber feature of the suction itself that could lend it to, I mean, just being replaced or something like that for adequate, and how that may have compared in your decision process to just possibly putting the C-clamp right on the edge of the tray and then having your bungee and stuff attached to that. Just thank you.
So the suction cups originally, we liked the idea of the suction cups because they were able to be placed anywhere along the tray. So you could have one large toy on the tray. He has one toy that basically takes up the whole length of his wheelchair tray, but then he has others that are smaller, and you could have numerous on the tray at one time. In terms of like wear and tear on that suction cup, it is a spring system rather than almost needing to be sticky. So the material of it is not adhesive at all. It's more all based off of the pressure, and it has the suction cup itself has, once you push it down, it locks that pressure. So it's not as much about like being adhesive to come up. That pressure needs to be released to even remove the suction cup from the tray. And if something were to happen with the suction cup, they are easily replaceable and then just screwed into the 3D printed part that is attached to our C-clamp. So if they ever need to be replaced, that's very easy to do. Anybody would be able to do that. Thanks.
Congratulations on your final presentation. And our next group is our tensegrity structure group.
We're ready. Good morning, everyone. We're Team 8. My name is Cesar, Juan, Jack, and EJ. This is our final presentation for a tensegrity structure deployment device. Our clients are Dr. Sue from University of Maryland, Baltimore County, and Dr. Yuan from University of Alabama. To give you some background information, the picture on the right shows the tensegrity structure we're working with. This tensegrity structure is a self-supporting stable structural system that consists of 6 solid bars, 18 strings, and 12 nodes. The goal of our project was to design a device that could keep the tensegrity structure compressed until our client was ready to perform his test so that he could deploy it. Some of the key system requirements were the device was not supposed to interfere with our client's experiment, the device was supposed to be attached to his workbench, and the device was not supposed to add any vibrations to the system. This is our prototype number 1, and with this prototype, we realized that a single hole was not gonna be able to hold the device to the table. The mid-plate was not gonna be able to hold the weight of the grippers. The Arduino microcontroller was not supplying enough power to the grippers, therefore there was slippage and lag. With prototype number 2, we solved the problems we had previously, but we encountered even more problems. So we realized that we needed to add, we come up with a better way to attach the tensegrity structure to the T-frame. The gripper locations needed to be adjusted. We needed to add a controller to control when the grippers open and close. We also had to build a case for the microcontroller. We had to redesign the midplate again, and we also had to build the wiring harness.
So the image on the left is our final CAD model. As you can see, we made the holes for our bolts and nuts so we can attach the servo grippers to the base. And then we attach a channel on the side of the base so we were able to attach that base into the workbench. On the figure on the right, you can see our prototype in person. That's the location for the servo grippers and the frame. To see if the frame and the base was gonna hold up, we ran an FEA analysis. On the picture on the left is the picture of the T-frame. We added about a pound of force, because that's when we compress the tensiometry structure down. It makes about a pound of force into the T-frame. So in order to decide if the T-frame was gonna hold up, we ran the FEA analysis, and we're way below our yield strength, so our T-frame was gonna hold up. The same concept on the right, we ran it with about a pound and a half, which was the total weight of the servo grippers into the plate.
So for the construction of our device, starting with the frame, we ended up going with 1060 aluminum. For the mid plate, the electronics, housing, and the control knob, we printed those out of PLA+. Additionally, the Arduino and the 3 servo motors run off of a 9-volt parallel circuit. And the control of the servo grippers themselves is accomplished with a 10K potentiometer. Also, in the device, we employ the use of a prototyping board to help make the connections a little more rigid and to aid in any future part replacement that may occur. Pictured on the left is an isometric view of the electronics housing. This gives you a better idea of the positioning of the components within the case. It also shows that the 2 components are raised to help with heat dissipation and to prevent any shorts that would occur while the circuit is powered on. And on the right shows the electrical diagram, the wiring diagram used in the circuit. It shows all 3 of the servo motors ran in parallel with the Arduino off of a 9-volt wall plug. So we have a video here that we took just a few days ago during our test and fitment at Dr. Zhu's lab. And the video is cut a little short, but we were able to verify that the device is able to hold its integrity structure in compression until prompted and then release successfully for testing. And on the right is an image of the entire assembly installed on site and ready for use.
During testing, we ensured that we supplied between 9 to 10 volts to our servo grippers and our Arduino as seen in the connection in the image. We also ensured that we did this to ensure that the servo grippers deployed as desired and that there was no delay in its operation. We attached Velcro clips to each teeth of each of our servo grippers to ensure that we had enough friction for the servo grippers to firmly hold the tensegrity structure when it was fully compressed. During testing, we also needed to figure out the precise location for the tensegrity structures on the mid plate, as well to hold the tensegrity structure at this right point, as well as where the position to drill the holes to the mid plate so we can attach the grippers to the mid plate. During testing of the Arduino code, we ensured that we had zero time milliseconds in delay, and we had different testing methods, as you can see on the slide, but we ended up using a potentiometer. So the budget for our product came to just about $140 without including the cost for 3D printing. Our major components included our servo grippers, the Arduino microcontroller, some nuts, and some bolts. So here is just a breakdown of the timeline of the entire project. We started the project in September after meeting our client. We had a few brainstorming ideas and what we needed to do to ensure that we had the right idea and the right approach for our product. In October, we started our first prototype and developed it, and in the middle of October, we had a second prototype developed. We had some setback in meeting up with schedules because we had a delay in our products being delivered, but in November, we started testing, and we were able to get back on schedule just right before the Thanksgiving break. After the Thanksgiving break, we've been up to schedule. We've had a test meeting with our client, and now we're on schedule to have this project completed on the final due date. Any questions?
Could you describe how the device actually holds the structure in its flattened form?
Yes, if we can go back to... So if you can see here, once the tensegrity structure will be manually compressed by our client, the servo grippers will be adjusted with a potentiometer. This will hold the servo grippers in place, We attached a Velcro clip just to avoid slippage because that was an issue in our first prototype. So once the client is ready to test in his lab, you can adjust the potentiometer just a little bit and it should freely deploy the tensegrity structure.
Okay, and then the delay, did you measure the delay any more precisely than it's effectively immediate? Is that? Was
Yeah,
that
so
important?
that's part of our testing on the upcoming weeks. We're still measuring the time delay of the servo grippers into the structure.
Okay. Do you have a way of, I guess it's probably important that all three release at the same time. Do you have a way of determining if that happened or not? Or
Yeah,
how
so we'll
close
be
they are?
using high-speed cameras to try to capture the moment as the servo grippers open. That way we can account for the delay to see what the performance is on them.
Okay, thanks.
I'm not super familiar with these structures, but I can imagine that there could be other configurations for them. Had you thought about different designs for the structures and how that would impact your design for its attachment and then release?
I'll answer that. So for this particular design, we had to work with the tensegrity structures that was provided to us by our client. So this is the model that they were using. Our client is collaborating with Dr. Sichen Yuan at the University of Alabama, and this is the current structure we're using. And just because of the time that we had to just design with this structure, the model that our client provided to us.
Thank
you. So this design is just for this model.
Congratulations on your final presentation. You also got some shout outs too. All right. Team number 9, Kinetic Sculpture.
Hi, my name is John Dixon Burke.
I'm CJ Escobar.
And I'm Jillian Taylor, and we are JC Hammerhead, and this is our final presentation. So a little bit of background on our project. We've been working with Dr. Stephen McAlpine, who works with the INDS department here at UMBC, and we're working on the MC Hammerhead Kinetic Sculpture, which competes in the Baltimore Kinetic Sculpture Race every year. This race has both land and water components, so our job has been to redesign the rudder system for the water component of this competition.
So just some issues with the previous design were that it didn't actually turn the structure in water, and it was powered by a pulley system that would interfere with the existing sculpture components. In addition, the connection between the front two tricycles, trikes 1 and 2, had collapsed in a previous competition, so we had to take that into account as well. And a little bit about our key requirements. Obviously, we want the rudders to turn the sculpture left and right. And we also don't want the components to interfere with the sculpture. And we also would like for the components to be primarily upcycled or recycled, but we can use new materials as well.
So our final system at a glance, we have 3 main areas of design. We have the redesigned connection point, the front rudder system, and the back rudder system. Because the tricycles are a segmented design, it's not a single solid structure, we're not confident in the ability of a single back rudder to properly turn the device around, so we implemented the front rudder system as a form of course correction. The rudder shapes, we originally went with a NACA 0012 airfoil shape. However, during our analysis and testing, we discovered that the shape of the rudder wasn't really affecting our abilities, just due to the slow speed. We're moving at less than ½ meter per second. So the rudders act more as drag paddles than an actual streamline rudder. So for the front rudder system, we have a few of our initial designs and prototypes, and finally we settled on a removable front rudder that uses a C-channel connection system that the pilot can reach down and pull up. So now we have our final design here. You can see the handle that the pilot can reach down and remove. The entire structure is welded together through that tube, and then it is attached to the handlebars up above. This makes it so the pilot can steer the rudder using the handlebars itself once they insert it.
Yes, so the next thing that we needed to consider was the connection between tricycles 1 and 2. So we had a few low and high fidelity models that helped us arrive at our final design, which was, next slide, yes. So we needed to consider how to create more room for this front rudder system. So we ended up utilizing the front of an upcycled suspension bike. We figured that this would better absorb the shock when they have the water impact and also remain movable in the rotational directions that Dr. McAlpine initially had designed for. And we connected this to Trike 2 by welding a steel strut to Trike 2 and bolting these components to that strut.
Moving on to the back rudder system, here's just some of our preliminary designs. Since this is at the very back of the sculpture, there wouldn't be any components that would prevent the rudder from rotating upwards when it's being stored. So this allowed us to actually have a bigger rudder blade at the back, which we wanted for our main steering. A little bit on our FEA on that final design. I'll get into those components in a bit, but you can see that under the load of the back rudder, there is very little stress on the system, so we don't have many concerns about any failure on it. On the left image, you can see what this final system actually is. That maroon piece is another upcycled head tube of a tricycle turned upside down, so that it's actually mounted via the handlebars. So that's rigid, while the head tube itself is actually the rotation point. And within that head tube, we've connected yet another fork. On the right image, you can see how the back rudder is mounted onto that fork, and this entire system is seared by the steel and bamboo piece.
So next, to go into our fabrication, we worked in the INDS makerspace, which had available to us a lot of recycled spare bike parts, pieces of metal, and scrap hardware. And due to the nature of the competition being really focused on recycling, we prioritized using these materials as much as we could and minimizing the amount of materials that we were purchasing. We did most of our work by hand, other than a few welds that were done by a professional welder, and we used tools like an angle grinder, reciprocating saw, and some power drills. And for our rudders, we ended up having an aluminum core that was upcycled aluminum plates connected together by steel bars and bolts, and then we wrapped chicken wire around this to create a frame for the airfoil, filled this with spray foam, and then shaved it down to create the airfoil shape, and covered both of them in duct tape to seal them off.
So a bit of our budget breakdown. Aside from all the materials that we already had on hand, here's just what we had to purchase. We had an allocated budget of $200, but we managed to spend only $171, putting us at 14% under budget. And here's our test plan. You'll actually get to see this implemented later on at our demonstration in the engineering building atrium. But it's just our plan of how we ride the sculpture into the water, deploy the rudders, perform the desired U-turn, remove the rudders, and get back onto land.
Yes, so for our testing, we first did a few land tests to ensure that our deployment of both of our rudders was successful and they could be steered by their respective handlebars, and these worked. And then we went on to do water testing, in which our first test, we got into the water and realized that despite researching that our foam would not float, it caused the rudders to float. So we exited the water and tried to strip as much of this foam as we could, and then went back in. And the front rudder was not able to deploy due to it still floating, but the back rudder actually did deploy about halfway, and that was effective enough to give us a very sharp 180-degree turn, which was successful. And we also were able to have all of our connection points maintain their shape in the face of the impacts.
So a bit about our test results. All of our specifications we completed under our expected, except for, of course, the front rudder deployment. Next slide. And finally, we have our very linear and streamlined timeline that showed the simple progression of our project. From initiation to concept designs, pre-production, fabrication that threw us for a loop, into the assembly, and we are finished with the design, and we just have to remove the rest of the foam and retest. Thank you.
On you because of the kinetic sculpture contest? Like
So-
maybe informing your material choices or other aspects?
So, let's see. We didn't necessarily have to use upcycled materials, but we already had so many available. We had maybe 4 bikes already in the makerspace for us to just tear apart and use. So that was more so convenience.
We weren't allowed to use any electronic components. Everything had to be mechanical. There's also an emphasis on ecology and not using materials that would pollute the water. And then also just in terms of design constraints total, we're working within an already established system. Certain things cannot be changed, like the trikes themselves all have to be able to rotate freely about one another. So that was one of the reasons behind the difficulties redesigning the connection point, because we needed space for that new rudder.
Thank you.
Oh, hi, Dr. McAlpine.
So, could you say a little bit more about placement of rudders? It's not a boat, so you have a very strange vehicle. How did you test for best intervention points, like where to place the rudders to maximize steering?
Yeah, so even though it's not a boat, we did want to put our main steering in the very back of the vehicle, but we also chose that intervention point between trikes 1 and 2 to be course correction and to allow for that independent turning about that point. In addition, we also know that trike 1 kind of leads the entire system, especially when the shark is attached to it, so we figured that it would be important to have the intervention point there.
Yes, and we also placed this front rudder between tricycles 1 and 2 because there are propellers on the back of tricycle 1, so we figured that this would cause a lot of water flow onto our rudder.
Early on, you talked about a design decision around a bicycle front fork with or without suspension. Was that out of convenience or curiosity, or did you find an actual advantage to that?
So we were taking a look at our existing forks because we wanted to maintain the existing connection point, which utilized forks, but obviously we didn't want it to collapse again. So since we had 2 suspension forks, this one in particular was made of a steel alloy. We felt that it would withstand that water impact better, and it did.
Yes, it also kind of had a truss already built into it with using the front of the bike, including that triangular section. So we thought that that would help make it a lot stronger when they enter the water.
Okay.
All right, did you have one more? Okay. We're running a little bit behind. We're a little behind, so we were going to say thank you very much. Congratulations on your final presentation. And of course, we will be heading to the atrium after this, so if you have any further questions, and also if you want to see the demos as well. And our final group, last but not least, come on out.
Hello, everybody. This is Team 10's Michaela Stool. I am Kyle Nikenji. I'm working with Colton Smith, Nathan Sipniewski, and Alex Tessa, and this is our project. So some of the backgrounds and requirements for the stool that we were making is for Michaela, she has a condition called postural orthostatic tachycardia syndrome, otherwise known as POTS, where blood pressure may require her to take a seat really quickly. So she would need a stool that needs to be unfolded, and it also has to be lightweight and ready to roll. It's custom built for her height, and we are also working with VME, volunteer medical engineers. Pictured on the right is our requirements that we had. Some of the most important requirements that we had was that the stool had to be under 10 pounds, and it also had to be able to roll, and it had to be unfolded in less than 20 seconds. And pictured on the right is our verification methods for each requirement that we had. Picture on the left here is our first initial design for the prototype. It's a little bit different than what we ended off with, but in the second picture is the prototype that we had. Prototype number 1 had failed the first time we had tested it because we didn't test it with the rivets. Then we added the rivets and made the seating more durable to sit on, and that's me sitting on it, and prototype 2 ended up working a lot better.
So this is our CAD model that we have. We have it when it's folded, and we have it when it's extended. And when it's folded, it stands tall at 25 inches. And then when it's wide open, it stands tall at 14.5 inches tall. Next slide, please. So this is our FEA analysis that we ran through. Before running this analysis, we know that our client weighed around 165 pounds. And for factor safety reason, we doubled the weight, which is a resulting force of 1,500 Newton force. And we apply a static load force of 1,500 Newton force. And the material selection that we chose was the alloy steel. And from the stress analysis graph, the maximum load force before breaking point is 2,700 pounds of Newton force. And this is really important for these design because like the safety is really important for our client, and we met the safety requirement for this design. Next.
So the main frame of the stool is a modified prefabricated frame called the Everywhere chair that's made of steel. The original Velcro straps were removed from their original positions and repurposed to become a locking mechanism when the stool is in its folded up position. In order to compensate for the extra height added by the wheels, 2 of the chair legs had their rubber stopper removed and some of the length was cut back using a pipe cutter. The original tabs on the frame were cut and filed smooth to prevent both user injury and tearing of the fabric. The seat of the stool is made of 420D Robic ripstock nylon. 4 layers of the fabric were cut and sewn together, and holes were drilled directly into the frame of the chair where the fabric was attached using 3 16th-inch aluminum rivets, 4 per side for a total of 8 rivets. We also used 3/4-inch washers to prevent further ripping of the fabric. The wheels of the stool are 7/8-inch expanding stem caster wheels. We chose to go with a stainless steel frame for its increased strength as well as its resistance to corrosion. The wheels are 4-inch polyurethane tread wheels to give it both indoor and outdoor capabilities, and they come with a total lock that allow the user to lock both the rotation and the swivel of the wheel. In order to attach the wheel, the expanding stem was placed directly into the open cut legs of the stool, and the interior hardware was tightened to expand the stem, this way pressure fitting it into the chair.
For the handle, we decided to use a foam-wrapped hard plastic handle with marine-grade polyester rope, and this provides a resilient handle which is comfortable to grip as well as being 29 inches in height from the ground to the handle. We attached the handle to the frame using rivets and washers in order to fasten the full diameter of the fabric or of the rope. And the handle allows the user to roll the stool comfortably without needing to bend over. Next slide. So for testing, we had Alex sit on the stool, fall onto it from the standing position to simulate free fall load of 170 plus pounds, and the stool remained stable and sturdy. And to follow up with that, we subjected the stool to a 350 plus pound static load, as can be seen in the image here. The stool requires less than 5 seconds to unfold, which is well within our requirement of 20 seconds, which means that our client will be able to open the stool without issue, even when she's feeling lightheaded due to her POTS situation. The stool weighs approximately 8.2 pounds, which is under the 10-pound requirement that we had, which means that our client will be able to carry the stool without issue when rolling is inconvenient.
The stool is able to roll while folded, which means that our client will have plenty of maneuverability as well as the option to roll and carry the stool. Next. So our budget, our materials cost for the final product was about $213, and this table shows a breakdown of that cost. The total cost for all of the materials throughout the entire semester was approximately $375 of our $700 budget, showing our team's effective cost optimization. And all that we have left is to deliver the final product to our client tomorrow. Next slide. Does anyone have any questions?
Could you, I don't know if you can back up easily or not, but on the budget slide, you said there was a total amount spent that was different than the material cost. What accounts for the difference?
Yes, so when we were making our prototypes, we actually had to order an identical frame that we ended up sort of destroying. We also ordered a different size wheel, and also a different fabric. So materials like that factor into that total cost.
Okay, so if you were to build a second one, it would be in 213, but you spent 375
Yes.
getting there. Okay, I understand that. And then on the load testing, I noticed in the photo, the wheels were not on the device in that photo. Have you done load testing with the wheels installed?
So we did do load testing with the wheels installed. Pictured in this picture right here, the wheels are not installed, but that's our second prototype. What we were trying to test was the frame and the rivets that we had just put in. In terms of testing with the wheels, we have done free fall testing with the wheels as well.
Okay. And do you have any sense of how strong that connection is between the wheels and the frame, given the loading condition that's maybe not quite as designed for that wheel?
In terms of like the wheel connection to the frame, with the expanding stem that we have and everything we have tested, because we've tested two different sets of wheels, both wheels connected and were strong with the frame that we had chosen.
Okay, thanks.
Can you talk a little bit about the strength of the fabric that you chose and how much margin you have?
The strength of the fabric. So the fabric itself is very strong. We did sorts of fatigue testing, free fall loads, and when we attach the washers using 4 rivets per side, it's almost impossible for us to tear it. It's very strong stuff.
The fatigue testing that we did was opening and closing the frame repeatedly over and over again. We were doing that for a very long time, and the fabric wasn't tearing at all. And we bought fabric that was specifically non-tear, ripstop nylon.
And then to add a little more detail into the fabric, so we use 420 denier Robic ripstop nylon. So our first prototype utilized regular ripstop nylon, same denier, which basically equates to the thickness of the fabric. And the thicker the fabric, the more durable and sturdy it'll be. And the difference between ripstop nylon and Robic ripstop nylon is it's roughly 50% more tear and abrasion resistant, so it's less likely to have any issues with failure.
Okay, thank you.
Congratulations on your final presentation. And with that being said, that concludes this part of our entire senior capstone day. We will be heading to the atrium. Please give the teams about 15 minutes to set up. Is that okay? Thumbs up? Awesome. And please congratulate them too. This was a lot of work for one semester. This is an overload class. So again, I'm going to give them all a round of applause for a fantastic job. And we will see you all in the atrium in about 15 minutes.